We're going to begin chapter 13 with reactions of arenes, and we're going to primarily look at electrophilic aromatic substitution reactions. Your electrophile, or E here, is going to be, remember, an electron seeker, so typically it's the positive portion of the molecule. It's going to replace the hydrogen off of the benzene ring. There are several different reactions we'll be looking at, so we'll look at each of these individually. And you should know what your electrophiles are for each of these reactions and what the final products are for these individual reactions. So let's first start with the nitration. On the nitration, you're going to see here is your nitric acid, just written a different way. And your electrophile is actually the nitronium ion. That would come from the nitric acid. The sulfuric acid is actually going to serve as a catalyst in this reaction. So the NO2 group is going to attach to the benzene ring, and of course the hydrogen is going to be given off and pick up the remaining part of the nitric acid, or the OH, to form water. The second reaction is sulfonation. You're going to use your sulfuric acid. Basically on this one, you also use a sulfur trioxide. That's actually your electrophile. So your sulfur trioxide is actually going to insert on initially, and then you will remove a hydrogen from your sulfuric acid in the mechanism to complete this functional group. And then the hydrogen off of the benzene will reform our catalyst, or our sulfuric acid. Our third reaction is our halogenation of benzene. You can either halogenate with the bromine or the chlorine. You will use a iron 3 compound, so iron 3 bromide is usually used with bromine, iron 3 chloride is usually used with the chlorine, but not doesn't have to be. And you're going to substitute on the halogen, whichever you have, onto the benzene ring. The hydrogen will be picking up the other halogen, in this case the hydrogen bromide will form. The electrophile in this case it's going to consist of the Lewis acid, Lewis base complex, which will be the bromine and the iron 3 bromide compound, or could be the chlorine and the iron 3 chloride compound. Should you want to attach iodine instead, we can use the acetyl hypoiodite, which is this molecule, CH3C-O-OI. And basically, you'll break the iodine off, it'll substitute on for the hydrogen, and this molecule that remains, or this ion that remains, will pick up the hydrogen and become a carboxylic acid. The Friedel-Crafts alkylation is where you're going to add an alkyl group. So the electrophile is the carbocation alkyl group. And you're going to use aluminum chloride. You could also use aluminum bromide, but this is what you typically see in the textbook. The chlorine will break off, it'll pick up the hydrogen from the benzene ring, and then your carbocation will attach to the benzene ring. Now this one's a little tricky because in this particular case, you do form a carbocation which can undergo rearrangement. So we'll look at an example where rearrangement may occur, just so you'll be familiar with that. Of course, in this particular case, it won't, because you have a tertiary carbocation, which is the most stable, and it wouldn't do any good to try to do any rearranging. But if I wanted to add on a long carbon chain, like a propyl group or a butyl group or something like that, then I wouldn't be able to go straight from or use a Friedel-Crafts alkylation directly to do that. The Friedel-Crafts acylation is this one where you have this molecule that has a carbonyl carbon and your halogen. So again, you'll break off the halogen, break off the hydrogen, again using aluminum chloride, and you'll form this molecule. Now these do not rearrange, so our electrophile is your acyl cation. So even though it's a cation, it doesn't undergo rearrangement. This is good to know because if I do want to make a long carbon chain, I can actually put on a acyl group, and then I can get rid of this, or I can reduce this carbonyl group in a reaction that we'll do a little bit later on called Clemenson's reduction, or the Wolff-Kishner reduction. So if I'm wanting to put on a long alkyl chain that won't rearrange, I'll have to go by way of Friedel-Crafts acylation first and then do a reduction reaction. You can also use acid anhydrides for this method as well. So here's an acid anhydride. Your general formula for acid anhydride is going to be this. So you'll break the bond at the carbonyl-carbon. So here's just an example. This is what's going to attach to the benzene ring by removing the hydrogen. The hydrogen that is removed is going to pick up the rest of this and form a carboxylic acid. Now the mechanism that's associated with your electrophilic aromatic substitution, the first step is you're going to attack the electrophile by the pi electrons from the benzene ring. So one set of pi electrons is going to pick up the electrophile and attach it to the benzene ring. What that's going to do is both electrons will go here to the electrophile, and that's going to leave us a positive region here, or a positive charge. If you'll notice, this is going to be an allylic carbocation. So it does reduce the stability of the benzene ring because it reduces the number of carbons that are involved in the conjugated system, but it's still a relatively stable type of carbocation. Our second step is you're going to undergo a deprotonation, or a loss of a proton from the carbocation. So here is our electrophile that was attached. Here's our positive charge. So we're going to get rid of this hydrogen. So when this hydrogen is removed, it's going to be picked up, of course, by like the chlorine or some other substance that's in the reaction. And then the electrons from that hydrogen are going to come in here and reform that benzene conjugated system. And this just shows you the energy of the reaction. All right, so I'm going to skip through a lot of this because we've already pretty much looked at these. So you can go back and look at these PowerPoints, and it's just going to show you some examples of the things that we've already looked at. I do want to look at the Friedel-Crafts alkylation and show you some examples of where you might have some rearrangement. So we've already looked at this one where you had the tertiary butyl carbocation. So that's not going to rearrange. So let's look at one where you may see a rearrangement of some sort. Okay, let's look at this one. On this one, we have an isobutyl chloride group. So here is we're drawing our structure out. This will be our isobutyl chloride. And if we remove the chlorine, then you can see that this would be our carbocation. So our carbocation is going to end up being a primary carbocation, which is not very stable. So what's going to happen is you can either do a hydride shift, or you could do a methyl shift. Or in some cases, you can even do an allylic rearrangement, depending on what your structure looks like. So in this particular case, if I have a hydrogen at the top up here, I can do a hydride shift by shifting this over to this carbon, which is going to shift the positive charge back to where the hydrogen is and create a much more stable carbocation, in this case a tertiary carbocation. So this actually forms the same thing that we started off with when we did the tertiary butyl chloride. Will form tertiary butyl benzene, just like we did with the tertiary butyl chloride, instead of forming an isobutyl benzene. So you have to be careful if you're trying to add on a carbon chain. You need to see if there is a way to make the carbocation more stable. If you want something that requires the fact that it does rearrange and you're not going to be able to form it this way, you're going to have to undergo the Friedel-Crafts acylation first. And I'll show you an example of that shortly. Now, Fritos Craft acylation uses acyl halides, and it's going to form aryl ketones. So here's examples. And we've already looked at this. So our electrophile here is our acyl cation, or it's called an Irelium ion. And of course, this would be the ketone. So I've got a carbon group over here, it's separated by a carbonyl carbon. Your basic mechanism is the same, so you can see that that's just your electrophile, so it's going to attach, and then you'll do a deprotonation. And as I mentioned before, you can also use acid anhydrides for this reaction as well. Now, this is a reaction where you can reduce the carbonyl carbon into a methylene group. So if I want to convert a carbonyl carbon into a methylene group, in other words, if I want to change a acyl group so that I end up with an alkyl group, then there's two mechanisms that we use, or two reactions that we use to do this. One is called the Clemenson's reduction. What this is going to do is it's first going to show us the Fritos Craft acylation process, putting on our carbonyl carbon, and then using a zinc mercury amalgam and hydrochloric acid, this is going to convert this carbonyl carbon to a methylene carbon. The other reaction that does the same thing, it's just going to use different reagents, is called the Wolff-Kishner reduction. This uses hydrazine, which is this compound, a base, a strong base, typically the potassium hydroxide, triethylene glycol, and heat. And it does exactly the same thing. It reduces this carbonyl carbon down to a methylene carbon. So it doesn't matter if you use a Clemenson's reduction or the Wolff-Kishner reduction, you're going to end up getting the same type of product. So if we, like I said earlier, if we have this molecule and we add it on to our carbon chain, then remember if we do a Fritos Craft alkylation, this is going to rearrange, and it's not really going to form this. It's going to form a tertiary butyl group instead. So if I want this isobutyl group on here, what I'm going to have to do is do a isobutyl group that has an acyl type region. Remove that chlorine, attach it first. So here's our isobutyl group here. And then I'm going to do a Clemenson's reduction using this, or I can use the hydrazine and the other compounds mentioned earlier for the Wolff-Kishner, and I can get the product that I want.